Okay, welcome to this video. We're going to talk about the pigeonhole principle some more in what I call the worst case scenario method. It's hard to really apply the pigeonhole principle in some of these problems. So I'd rather think of what would be the worst case scenario and then try to count from there. So we'll go through an example or two to illustrate what I mean. So for example, how many cards must you pick from a standard 52 card deck to be sure of getting at least one red card? So I'll set up the two diagrams and the mapping between them. So for example, we have our card set X. So those are our cards. And then we have the colors. So we have C1, C2, all the way through C52. And the colors we have red and blue. And if you're familiar with a 52 card deck, we know that, for example, 26 are red and 26 are blue. In other words, if I kind of fill out this drawing a little bit better, we have C through 26 and then C27. And you can think of it like red here has 26 of them, and they're all going to there. And then blue has 27 through 52, and it's all going to blue. And while you could pick up a red card in the first card that you pick up, right? Like I say, you have the 52 cards in a line. It's possible that this first one's red. It's also possible that, maybe this one's blue and then this one's red. But they're asking, in the worst case scenario, how many cards must you pick up to be sure 100%, no chance, that you're going to get the one red card, at least one red card. And what that means is you want to think of the worst case scenario. The worst case scenario in this situation is I take all the blue, so take all 26 blue, and then on the 27th card, you are guaranteed a red. And so that's what I mean when I think of the worst case scenario. While it's possible that I get a red card before then, they want to say, how many cards do you need to be sure with absolute no chance, or no chance in play, or in other words, 100% probability. Okay, so in summary, you need to take 27 cards to be sure that you get at least one red. Pretty intuitive. Right, here's another problem which we're going to apply that worst case scenario. So you're in line to get tickets to a concert. Each person can get at most 5 tickets. There are only 200 tickets available. And the person in line behind you says, I sure hope there are enough tickets for me. You're lucky though, you'll get as many as you want. So what does she know? And under what circumstances will she get any tickets? So we'll just give this person name, I'll just call her, I don't know, Andrea. And here you think of your set of tickets. So that's your X. And then you have your set of people. So Y is your people. So you have ticket 1, ticket 2, all the way to ticket 200. And then you have person 1, person 2. You don't know exactly, there's no information on where you are in line, but you know that you're somewhere in this line. So that's you. And then let's say person behind you right there. So that's the girl behind you, Andrea. And then there may be more people in the line. And she says that you're for sure going to get as many tickets as you want. And that each person can get at most 5 tickets. So I want to go through piece by piece what these kind of mean. So each person get at most 5 tickets. what does that mean in terms of kind of a set notation? So that means, let's look at kind of the worst case scenario for T1, meaning, okay, how many people are going to get T1, T2, T3, T4, and T5? Well, in the worst case scenario is her situation, or yours in line. The worst case is that they all take, person one takes tickets 1, 2, 3, 4, and 5. So what that's saying is the set Ti in X such that f of Ti equals P1, the size of this is, well, technically it's less than or equal to 5. In what I just drew, it is 5. So the worst case scenario is the one that equals 5. And this set notation you'll want to get comfortable with. In the next video, I'll be going over it some more. But basically it's saying the size of the x's, the number of x's that are going to get mapped to, so this is the function, mapped to person 1 is less than or equal to 5. And they could be any of them without loss of generality and simplicity. 1, 2, 3, 4, and 5 are the easiest ways to count those. Okay, and so that's what that green piece is saying. Each person can get at most 5 tickets. That's what that means. All right, so back to our goal here. She's saying that you're for sure guaranteed to get 5 tickets if you want as well. So what does she know then? Well, again, try to think of a worst case scenario. That means all of us here, we get our 5 tickets. It's like the worst case scenario for her because she's in line. She wants to make sure she gets her tickets. If we're taking as many tickets as we can, that leaves less for her. And she's saying that we can get our 5 tickets. So there's 200 tickets total. P1 gets 5. P2 gets 5. And you get 5. So where must you be in line then? Think of the scenario then where she's not going to get any tickets, so that we exhaust all the 200 tickets. So think of the scenario, truly is worst case scenario for her. You take the last 5 tickets. Well, she must know then that you are 40th in line. Because if I'm 40th in line, then P1 plus P2 plus P3 plus you, the number of tickets that we're each getting is 5 plus 5 plus 5 plus 5. And we know that the scenario is that we all take the 200 tickets. Then there must be 40 of us in line. Because 40 times 5 equals 200. So that's what she must know. So what does she know? She knows that you are 40th in line. And then under what circumstances will she get any tickets? Before we tackle that, I want to talk about, just re-emphasize. So let's say if there were more than 40 people, taking the max tickets. So if there are more than 40 people taking the max tickets, then there would be greater than 40 times 5, which is 200 tickets, right? If there's more than 40 people here, let's say this is 40, and there's more of us, and each of us are taking our 5 tickets, then there's more than 200 tickets total. Which leads us to then say, in what scenario will she get her tickets? Well, a couple scenarios. Scenario 1, she'll get at least 1 ticket. If there are less than 40 people in front of her. How do I know that? If there's less than 40 people in front of her, let's say, like, for example, let's say there's 39 people, and we're all taking our max. Kind of the worst case scenario for her. 39 times 5, and I believe that is 1 less than 200, so 195. So in that scenario, she's next in line. There's 200 tickets total. 195 tickets have been taken, so she can still take some tickets. Or, and this is inclusive, scenario 2, and scenario 1 and 2 are not mutually exclusive, meaning they both could happen. Not everyone, not all 40 people take the max. Right? That's what you would hope if you were her. She's in line and she's worried she's not going to get tickets. She's hoping that not everyone is going to take the max. And if there's 40 people and not everyone takes the max, she'll still have some left over. Because 40 is not going to be times 5 anymore. Right? Some are taking 5, so person 1 may be 5, person 2 may be 5, person 3 maybe that's 4. And then if you get all the way to person 40, let's say everyone else takes the max, then you'd be at 199 tickets. Remember, person 40 is you. And then the girl, Andrea, she'd still have at least 1 ticket. All right. So in either of those scenarios, and they are inclusive, she'll be able to get at least 1 ticket or more. And she knows that for you to guarantee to get your 5 tickets, you're person 40. So some of these problems can be thought of in this kind of worst case scenario method. Put your point of view from someone or something in the problem and just go through, exhaust the worst case scenario, and then try to count the outcomes from there. All right, in the next video, we're going to be talking about the generalized pigeonhole principle and its contrapositive. We'll be talking about it in the abstract set function theoretic framework. So it'll be a little abstract, but then we'll apply it to some examples. See you then.